The moon is the largest and brightest object in our night sky, when it's actually there, that is. It's Earth's only natural satellite, and it makes the planet more livable by stabilizing its wobble on its axis to make the climate more stable. The moon is also what causes tides on Earth. It's simply called the moon because for a pretty long time, no one even knew that other planets could have moons. Then that all changed when Mr. Galileo Galilei observed 4 moons orbiting around Jupiter. In Latin, the moon was called Luna, which is now part of our adjective for all things moon-related. Lunar. Let's dive deeper and take a closer look at our moon, shall we? The moon orbits Earth at an average distance of around 239,000 miles, although this number can change. At perigee, or its closest point to Earth, it's about 224,000 miles away. At apogee, or its furthest point from Earth, it's instead about 251,000 miles away. I may have said both of those words wrong. About 30 Earth-sized planets could fit between us and the moon, which really puts into perspective how far away it is. The moon makes a complete orbit around Earth every 27 days, and it makes a spin on its axis in the same amount of time. Because of its synchronous rotation, the moon is tidally locked to Earth, and we only ever see one side of it. Because Earth is also moving by rotating on its axis and orbiting around the sun, the moon appears to make an orbit around us once every 29 days. The moon is tilted on its axis by only about 1.5 degrees. This tilt is so small that our little rock friend doesn't experience any seasons. The moon has a radius of about 1,080 miles, which makes it less than a third of Earth's width. It's closer to about a quarter of the size of Earth. It can be divided into 3 layers: the core, the mantle, and the crust. The moon's core is solid and rich in iron. It's about 149 miles in radius, and it's surrounded by a liquid iron shell about 56 miles thick. Outside that is a partially molten layer about 93 miles thick. Although the core is primarily iron, it could contain large amounts of sulfur and other elements. The mantle is about 825 miles thick, extending from the top of the partially molten layer of the core all the way to the bottom of the crust. It's most likely made of minerals like olivine and pyroxene. These are made of magnesium, iron, silicon, and oxygen. Finally, there's the crust, which is about 43 miles thick on the moon's near side and around 93 miles thick on its far side. It's made of oxygen, silicon, magnesium, iron, calcium, and aluminum, with small amounts of titanium, uranium, thorium, potassium, and hydrogen. You might think that's a lot of elements, but just wait till you hear about the rest of the periodic table. The moon once had active volcanoes, but all of them are now dormant and haven't erupted for millions of years. Or maybe billions of years, I don't know, I just work here. The moon is perhaps most famous for its surface, which is covered in craters from impacts by asteroids, meteorites, and comets. Its atmosphere is insufficient to impede impacts, which is what leads to all of these craters. Over time, these repeated collisions have kind of ground up the moon's surface into fragments. These fragments range pretty widely from huge boulders to fine powder. Almost the entire moon is covered in something called the lunar regolith, which is a mix of dust, broken rock, and material. Underneath the lunar regolith is some fractured bedrock called the megaregolith, which will be the name of my new metal band. The light areas of the moon are known as the highlands. The dark features are called maria, which is Latin for seas. These areas are impact basins that filled with lava between 4.2 and 1.2 billion years ago, which is long before anything currently on this planet was alive. The moon's surface also has some remnants of humanity's visits, including equipments, American flags, and even a camera that some astronauts left behind. Imagine being halfway home from the fucking moon and being like, ah, damn it, guys, I forgot the camera. The temperatures on the moon can vary pretty wildly. Parts in sunlight can reach temperatures of 260 degrees Fahrenheit, which is way more than a human can live in. On the flip side, in darkness, temperatures can drop to negative 280 degrees Fahrenheit, which is still far too extreme for humans to survive. So either you get boiled, or you freeze. It's your pick. The moon has a very thin and tenuous atmosphere called an exosphere. This thing is not breathable, and it provides no protection from solar radiation or impacts. The exosphere contains helium, argon, neon, ammonia, methane, and carbon dioxide. Interestingly, it also contains sodium and potassium, which usually aren't found as gases in the atmospheres of Earth, Venus, or Mars. The source of the moon's exosphere is pretty much unknown. We're not really sure why it's there at all. The early moon might have developed an internal dynamo, which is the mechanism by which terrestrial planets generate a global magnetic field. Today, though, the moon has a very, very weak magnetic field, and Earth's is stronger by many thousands of times. There's a number of theories about how the moon came to be. For one, it might have formed somewhere else in the solar system, and it was later captured into orbit around Earth. Maybe it was created alongside Earth when the solar system formed. Maybe in its early days, Earth was spinning so goddamn fast that some material broke off and started orbiting it. Or hell, maybe Earth even stole the moon from Venus. Despite all of these theories, though, there is one that is far more widely accepted than any of them, and that is the large impact theory. Per the theory, about 4.5 billion years ago, so very, very early into the solar system's history, another planet collided with Earth. This hypothetical planet is now called Theia, and it would have been about the size of Mars. The collision caused debris from both Earth and Theia to be ejected into space. This debris then came together to form the moon. This process could have taken as little as 40 years, which may sound like a decently long time to us, but is absolutely nothing on a cosmic timescale. The newly formed moon would have been in a molten state, but within about 100 million years, most things would have crystallized. Less dense rocks would have floated up to form the crust. Moon rocks that were brought back from the Apollo missions showed that Earth and the moon have a lot of surprising chemical and isotopic similarities. These similarities cast doubt on the capture theory, because why would the two be so similar if the moon formed in a different part of the solar system? The rocks also make it seem less likely that the moon was formed from material ejected from a rapidly spinning Earth. If it came directly from the Earth, then the proportions of materials in both should be nearly identical, but they're actually somewhat different. And what happened to Theia, you might ask? Well, it was destroyed in the collision. But pieces of it still exist in the moon, and there might still be parts of it in Earth. Remnants of Theia could exist as unusual blob structures in the Earth's lower mantle. These blobs are called large, low shear velocity provinces, which is a hell of a mouthful. So yeah, that's probably why we have a moon. Something big crashed into us, and now we've got a little friend following us everywhere. Isn't that great? Tides are predictable changes in the sea level that are caused by the moon's gravity pulling on Earth. High tides are water bulging up from Earth's surface. They occur on the side closest to the moon because of the moon's gravity, but also on the farthest side because of the inertia of water. Low tides, on the other hand, occur when water levels drop, and they appear between high tides. The tides are causing Earth's rotation to slow and the moon to drift further away. The moon raises tides on opposite ends of Earth, but because Earth spins faster than the moon's orbit, it carries these tides a little ahead of the moon's position in its orbit. The gravitational pull of this lump of water accelerates the moon a little bit and causes it to drift a teeny bit higher. Because the moon, in this case, through acceleration, is gaining energy, the Earth loses some and its rotation slows. The moon is drifting away at a rate of about 1.5 inches per year. The Earth's day increases in length by about 2.3 milliseconds per century. One day far into the future, Earth could become tidally locked to the moon, meaning that the moon will only ever see one side of it. It was probably this very same process that resulted in the moon becoming tidally locked. Do we need to worry about ever losing our moon? Nope. Even at the current rate, the moon would take so long to drift out of orbit around Earth that the sun will die and eat us both first. And what a fiery end that'll be. The phases of the moon result from its orbit causing different parts of it to be in sunlight or darkness at different times. The two ends of the lunar cycle are the new moon and the full moon. With a full moon, the visible hemisphere of the moon is completely illuminated by the sun, while a new moon is the exact opposite. The moon is not visible during a new moon. There are several other phases to the moon, though. If we start at a new moon, the next phase is a waxing crescent. After that is the first quarter, or a half moon. Then we have a waxing gibbous. Next is the full moon, after which we have a waning gibbous. Then it's the third quarter, or another half moon, except the other half of the moon is illuminated this time. Then we have a waning crescent, and then we're back to a new moon. For the most part, only the sunlit portion of the moon is visible. But sometimes, during the crescent phases, the unlit part can be seen a little bit. This is from a phenomenon called Earthshine, in which sunlight reflected off of Earth illuminates the moon. As you've probably seen yourself, the moon can be visible during the day. This is most likely to happen during the gibbous phases, and it never occurs during a new or full moon. The moon can never be seen during a new moon, and with full moons, it is always below the horizon during the day. Eclipses are a neat little thing that happens when the Earth, moon, and sun are in a nearly straight line. There's two main types of eclipses: lunar, and solar. During a lunar eclipse, the Earth is directly between the sun and the moon, casting its shadow onto the moon's surface. This can only occur during a full moon. There are 3 types of lunar eclipse. In a total lunar eclipse, Earth's shadow is cast across the entire lunar surface. In a partial lunar eclipse, only part of the moon enters Earth's shadow. In a penumbral lunar eclipse, the faint outer part of the Earth's shadow is cast onto the moon's surface. This type is much less dramatic and can be harder to see than the other 2. During a total lunar eclipse, the moon takes on a sort of rusty red color, which is what earned it the nickname Blood Moon, and that will be the title of my metal band's first release. The red color is caused by the interaction between sunlight and Earth's atmosphere. The atmosphere scatters and filters different wavelengths of light. Shorter wavelengths like blue are scattered outward. Longer wavelengths like red are bent or refracted into Earth's umbra, or the darkest part of its shadow. When the moon passes into the umbra during a total lunar eclipse, these longer wavelengths are reflected off of its surface. About 3 lunar eclipses occur every year, and around 29% are total. From any given location, you can see a total lunar eclipse on average about every 2.5 years. They usually last for a few hours. Next is the solar eclipse, in which the moon passes between the Earth and the sun and casts its shadow onto Earth's surface. This can only occur during a new moon. There are 4 types of solar eclipse. First is the total solar eclipse, where the moon fully obscures the sun. This is possible because the sun's diameter is about 400 times larger than the moon's, but it's also about 400 times further away, and it's incredible that the numbers worked out perfectly like that. In a partial solar eclipse, the moon does not fully block the sun. This happens when the trio of bodies is not fully aligned. With an annular solar eclipse, the moon is centered in front of the sun, but it doesn't block its entire surface. They're also called ring of fire eclipses because it looks like a ring of fire is burning around the moon. Annular eclipses happen when the moon is near apogee, or its furthest point from Earth, and I probably said that word wrong again. Finally, we have hybrid solar eclipses, which are a combination of total and annular eclipses. These happen when the Earth's shadow moves across Earth. They begin as one type of eclipse and then transition to another. Hybrids are the rarest type of eclipse. The eclipse season happens about twice a year when the new moon aligns itself in a way to eclipse the sun. But solar eclipses don't happen on every new moon because the moon's orbit is tilted about 5 degrees with respect to Earth's orbit around the sun. This causes the moon's shadow to usually pass above or below Earth. There's a total solar eclipse coming up on April 8th of this year. You can look it up online to see if you're within the path of totality or the area in which you can actually view the total eclipse. If you're a little outside of it, you might instead see it as a partial eclipse, which is still pretty neat. This won't be a surprise to anyone at this point, but I love the moon. I've always loved the moon. I think it's so neat that it's just this little rock friend that's pretty much always been there throughout Earth's history and will probably stick around until we're both killed by the sun. I hope you love the moon as much as I do, and I also hope you enjoyed my dumb little video about it. Thanks for sticking around, like and subscribe if you enjoyed and want to see more, and I'll see you next time.